Hi. It's always a pleasure to be back here in Santa Cruz. Thank you very much for everyone who keep inviting me back for some reason. But I'm very grateful. And today I'm going to talk to you about something completely different, kind of unrelated to anything we've heard about so far. Much, much larger scales, not talking about actual galaxies, but zooming out into the intergalactic medium, and specifically the shattering of cosmic sheets. And I'll explain to you what that means. This is work in collaboration with Frank van den Bosch, who's in the audience, as well as with Volker Springel and Freke van der Voort, as part of the, I suppose, the former HITCL program in astrophysics. So a brief overview, just because this is kind of off the main topic of what we've been talking about so far. Why do we care about the circumgalactic medium or the intergalactic medium? So at least one thing that you could kind of take away, and I'm sure we'll be hearing a lot more about this tomorrow, is that most of the baryons, and in fact most of the metals in the universe, are not located inside galaxies. They're outside galaxies. They must be in what they call the circumgalactic medium, which is a space outside a galaxy but still inside the virial region, or the intergalactic medium, which is a space outside the virial region. This is taken from Tomlinson et al. This is showing the contribution to the baryons from stars and from interstellar gas compared to the mean, compared to the universal mean baryon fraction. This is showing the fraction of the metals that you would expect to find given the star formation history and the metal yields. This is a total metallicity that you would expect to find in a galaxy, and these are observed the metals in stars and gas and in dust. As you can see, we fall significantly short, which means that most of the matter in the universe is not in galaxies. So if you want to be able to understand the universe using cosmological simulations, we'd better be able to actually resolve stuff outside of galaxies. However, that's not as easy as you might think. And this is very nicely illustrated in this paper here by Dylan Nelson, 2016. Since the typical refinement is usually what they call quasi-Lagrangian, in other words, a fixed mass, as you go further away from the galaxy and your density gets smaller and smaller, the cell sizes become larger and larger. And in fact, even if you could report a minimal cell size, a maximal spatial resolution in your galaxy of 3 parsecs, once you go out near the virial radius, that's basically the kind of typical cell size grows by a factor of 1,000. It becomes to be the scale of a kiloparsec. Now you might ask, well, who cares? I mean, if the density of the gas is so low, maybe I don't need such high resolution to resolve it in the first place. What scale am I trying to resolve? Well, actually, it turns out that there is a spatial scale that we want to be able to resolve, and that's what's known as the cooling length. The cooling length is the sound speed of gas times the cooling time in the gas. And it's basically the largest scale that a cloud that has to cool, that's significantly far from thermal equilibrium, and it has to cool, that's the largest scale that can cool coherently in pressure equilibrium. And as was extremely nicely shown in this paper by Mike McCourt, where you have a cloud that's a lot larger than the cooling length, the end result is that it shatters into several cloudlets that each are of order the cooling length. So if we really want to be able to fully resolve the physics of the cooling and to get a handle on how much cold gas we have in the CGM and the IGM, we should be able to resolve the cooling length in the CGM and the IGM. The problem is the cooling length is quite small. It's of order like 1 to 10 parsec scales in the CGM. And that's very hard, as we saw, to get that kind of a resolution in the CGM using standard methods. As a result of that, there have been a number of different efforts over the last 2 years to try and get much better spatial resolution in the CGM. And here I'm showing you one example from that was published by Freke and our group, but as I said, there are quite a few others. And what we did here, this is using a repo code. This is a standard zoom-in simulation of a Milky Way halo with what they call standard like mass refinement. And here we've done something in addition where we don't let the cells in the halo, regardless of how low the density is, we don't let the cell size become larger than either 2 kiloparsec or 1 kiloparsec. Now when you look at the total column density of hydrogen, there really isn't much difference, but when you look at the column density of the neutral hydrogen, already by eye, you can see huge differences. All right, and it's put a bit more quantitatively. Oh no, this is supposed to come up later. Oh well. So what I'm showing you now is the covering fraction as a function of the neutral hydrogen gas. And as you go from the standard mass refinement simulation to the 2 kiloparsec volume refinement to the 1 kiloparsec volume refinement, you go, oh, isn't this cool? We suddenly match the Cos halos observations because the neutral hydrogen column densities have gone way up. But then you go to even higher, only 0.5 kiloparsec resolution, you go, oh no, we're actually way overshooting the cost of those observations. Now, this is not converged. It's not surprising that it's not converged because we're still really far away from the cooling length. But it's actually good that we're not matching the observations because now we can learn something about feedback, about cooling, about self-shielding, and all this stuff that we kind of don't really know and can't really constrain all that well using the galaxies themselves. We can suddenly constrain much better using the CGM and the IGM. And as I said, there are a few other groups, and we all find, to a certain extent, very similar things. But what about the IGM? I've talked to you about the CGM for the last, 2 slides. This is a plot from the Suresh et al. Paper. This is showing the gas cell mass as a function of galactocentric radius. The only thing I want you to take away from this is even when you have really cool additional CGM refinement, once you get to the intergalactic medium, which is outside the zoom-in region, the resolution becomes really bad again. So even these really cool new methods that are trying to get a lot of spatial resolution in the halo, they've been ignoring what lies outside of the halo. And that's where we come in. So what we wanted to do is to zoom in on the intergalactic medium. Now, how do you do that? What did we set up? Well, we took the illustrious TNG 100 simulation, and we selected each and every halo at redshift 2.3 that had a virial mass larger than 10 to the 12 solar masses. And we looked at all basically pairwise combinations of them, and we found about 50 that had a separation in this mass range, which at redshift 2 is a little over 1 megaparsec. We selected one pair at random, which turned out each halo had a virial mass of about 5 times 10 to the 12, separated by just over 1 megaparsec, and they were connected by a giant large-scale cosmic web filament of dark matter. And then we said, okay, our zoom-in region now is going to be this entire thing, the 2 halos and the filament that's connecting them, which is defined here kind of, quite technically by a cylinder plus 2 spheres. But this is a much larger zoom-in region than any other simulation that has been done so far, and we basically simulated this at 5 different mass resolutions, ranging from something comparable to the TNG 300 simulation to a mass resolution that's 10 times better than the TNG 50 simulation. Now I'm going to show you a movie. I'm supposed to show you a movie. Oh, God, that's why it wasn't working. I'm so sorry. Wow. My apologies. Hang on, let me... excellent. I'm so sorry. Okay. This is going to loop around so we can watch it a few times. What you're seeing on the top is the gas density, and what you're seeing on the bottom is the gas temperature. And this is a movie from redshift 7 down to redshift 2. And what you can see is that... What you can see is that you start out with basically 2 sheets in the gas. You know what? Let me try and get this to play again. My apologies. One last try. There you go. So as you can see, at some point you get 2 cosmic sheets that basically collide. And when they collide, there's an accretion shock surrounding the cosmic sheet, or the Zeldovich pancake, as it's sometimes called. And within the I don't know why this stops, but anyway, within the pancake, you have a lot of very dense cold filaments, even though the surrounding medium, I'll get back to that in a second, becomes very hot. Now, what I want you to notice is just as the 2 sheets begin to collide, you see this wave, a very granular-looking material that seems to propagate following the collision between the 2 sheets. And it's that granular kind of structure which we found very curious, and we wanted to investigate what exactly is going on here. So we started studying what will forever be known as the IPM, or the intra-pancake medium. If you remember nothing else in this talk, remember intra-pancake medium. And this is a snapshot at redshift 5, redshift 4, and redshift 3. This is looking at that giant cosmic sheet in an edge-on view and a face-on view where you can see all the dense filaments. All the black circles are each and every dark matter halo that has a virial mass that's either 10 to the 9 solar masses or above. You can see they basically all lie along the filaments. The filaments themselves begin to merge as the massive halos merge. The filaments themselves also begin to merge, so you can really see the growth of large-scale structure and the evolution of the cosmic web. And here, I'm zooming in on these 3 regions that I've marked, and now I'm showing you not the total hydrogen column density, but the neutral hydrogen column density. As you can see, there are a lot of regions which can be classified as Lyman limit systems that have a neutral hydrogen column density above this number, 10 to the 17.2. Now, why should that be interesting? give me a couple of slides, but this is actually very interesting. Looking at it in a bit more different properties. So this is a snapshot at redshift 4 that we had just found. Here I'm zooming in on this region called S1. This is the total hydrogen column density, the neutral hydrogen column density. Here you can very nicely see all the Lyman limit systems that we have here. This is the dark matter surface density, which is not at all very interesting. If anything, it's an underdense region of dark matter. And all these circles are even the lowest mass dark matter halos that we can resolve. There's nothing here in terms of the large-scale structure in the dark matter. What's also very interesting to note is that the metallicity in this region is basically 0. Now, it's not surprising because we're really far away from any massive galaxy. So you don't expect it to have been pre-enriched by metals. Now, why is this interesting? I'll come to that at the end. This is actually very interesting. So what exactly is going on here? Well, what's going on here is we're triggering thermal instabilities. Once those two sheets collide and they send that strong shock wave that we could see in the movie, what we're doing is we're shattering the cosmic sheet due to the method proposed by Mike McCord et al., which we talked about. What I'm showing you here is in that same sheet region that we've zoomed in on, a phase diagram, the temperature and the density. This is weighted by mass, this is weighted by volume. You can quite clearly see lying along a constant pressure line, we have, most of the mass is in a kind of a cold and, dense phase. Most of the volume is in a kind of a hot and a less dense phase. And if you look at the cooling length in this same plane, the post-shock region, which is around here, the post-shock region has a cooling length of order 10 kiloparsec. Now, the blue histogram, this is a histogram of cell size in that region. The blue histogram is a simulation that has a resolution comparable to TNG 100. And the typical cell size in this region is about 4 kiloparsec. So we can't even resolve the cooling length in the post-shock region, never mind the cooling length in the dense phase, which is of order 1 kiloparsec. So you don't get any of those small, cold, dense clouds that we saw. But in our highest resolution simulation, we can actually get a median cell size of less than 1 kiloparsec, a minimal cell size of about 300 parsec just in that region. So the cooling length in the post-shock region is very well resolved, and even the cooling length in the cold phase is marginally resolved. So this is also likely not yet converged, but we're getting there. This is a movie kind of going through, showing individual slices, going through the sheet in that region that we've zoomed in on, showing the volume density and the temperature, just so that you can see the shattered structure of the kind of cold and dense clouds embedded in a hot, more dilute medium. And the typical size scale of these clouds is of order 1 kiloparsec, which is what you would expect from the cooling length argument. Although, again, this is likely not converged because we just barely resolved those 1 kiloparsec scale clouds. This is looking at a slice through the midpoint of the sheet in our highest resolution simulation, where the cooling length in the post-shock medium is very well resolved, as opposed to with TNG 100 resolution, where you can't even resolve the cooling length in the post-shock medium. And the difference is quite striking. You don't form those high-density shattered cloudlets when you can't resolve the cooling length. This is now showing you the neutral hydrogen column density in a simulation with comparable resolution to TNG 300. Nothing special. You go to TNG 100, not really anything special. TNG 50, you can begin to see a few Lyman limit systems. And if you go to a highest resolution simulation, you really see a lot of very dense gas that is Lyman limit systems. Now, I said, why is that interesting that we're finding Lyman limit systems deep in the intergalactic medium with 0 metals? Because they've been observed, and it's been kind of weird. Several Lyman limit systems have been detected with very low metallicities, less than 10 to the minus 4, which implies that they could not have been polluted by even a single POP3 supernova. This is estimated to be about 1 to 2% of the Lyman limit system population at redshift about 3 to 5. And here I'm quoting from the paper by Robert et al. It may be that all Lyman limit systems have the same origin, with the common assumption that they arise in the CGM. On the other hand, these very metal-poor Lyman limit systems may arise in a different environment, for instance, in the intergalactic medium. This has also been proposed by completely different arguments, using number count statistics, by Fumagalli et al. 2013, who said that above redshift 3, you would need a contribution to the Lyman limit system population to arise not in the CGM of galaxies, but deep in the IGM. And our simulations now, for the first time, are showing a method of how that might happen. This is showing just the covering fraction as a function of the H1 column density. This is the Lyman limit system threshold. This is at redshift 5, redshift 4, and redshift 3. The dashed lines of the TNG 100 simulation, where basically by redshift 4, the covering fraction of Lyman limit systems with 0 metallicity that are not associated with dark matter overdensities, which actually has possible implications for the Lyman alpha forest, because we typically assume that Lyman limit systems are associated with large overdensities in the dark matter. But here, in our Zoom simulations, we have at redshift 3 to 4 about 1% covering fraction and about 35% covering fraction at redshift 5 of these new unique systems. Now, the final point I'll make is, what about Lyman limit systems in streams? This has actually been proposed in the past by several authors. Streams are not going to have metallicities less than 10 to the minus 3. There are a number of works, including our own, which show that the metallicity in streams gets enriched to about 10 to the minus 3 or above at very high redshift already. This is a snapshot at redshift 4. To get those really low metallicity Lyman limit systems, you need to go in between the sheets into the IPM. So just to summarize, traditional simulations do not resolve diffuse gas in the CGM or the IGM. Numerous recent works have tried to introduce new methods to resolve the CGM to a few hundred parsecs. This has large effects on the distribution of neutral hydrogen, and they're not yet converged because they're still far from resolving the cooling length. New simulations, which we've just discussed, zooming in on the intergalactic medium between two massive halos, we can see cosmic web evolution, intergalactic pancakes, collapsing and shock heating contain cold filaments, which all the galaxies lie. The filaments merge within the plane. The post-shock region in collapsed pancake is thermally unstable, forming hot and cold clumps in the pancakes. And it shatters if the cooling length is resolved. And this is likely independent of galaxy formation subgrid physics because we're so damn far away from galaxies, which is really cool. This leads to Lyman limit systems in the IPM with primordial composition similar to observed systems, and it might have potential implications for Lyman alpha forest and a relation to the matter power spectrum, which is something that we're working on at the moment. Thank you. So since the overall densities in the sheets decrease with redshift, so this is not these sheets are not really virialized. So their density is effectively going to go down as the cosmic with the cosmic evolution. So you're not going to get these Lyman limit systems. In fact, you can even see that the covering fraction just from Z of 5 to Z of 4 drops quite a bit. From Z of 4 to Z of 3 drops, and down to Z of 2, even in a high resolution simulation, is basically 0. Correct. No, but effectively, any Lyman limit system that's in a sheet in between the filaments is likely to be primordial because it's very hard to get the metallicity outside of the filaments. So I think the question of a basically primordial Lyman limit system or a Lyman limit system in the IPM is basically the same thing. So the question is, how dense is the IPM? And you're going to all remember that. How dense is the IPM, and can you form a Lyman limit system there? And I don't think you expect to see that at redshifts less than 3, which is also consistent with when you stop seeing these basically zero metallicity Lyman limit systems. You don't see them at redshifts smaller than 3. And I think that's basically related.
So your column density looks quite high for the zoom-in simulation, such that should we have seen this already in existing observations? Have we not? Detection threshold such that should we be looking for an archive as opposed to the other?
Well, as I've tried to point out, we have been observing some of these, basically zero metallicity Lyman limit systems. I don't think you're going to get into the damped Lyman alpha regime. Damped Lyman alpha regime is about 10 to the 21. You're not going to get there in the sheets, no matter what you do. So what I don't yet have is an extrapolation of this plot to kind of what I expect the universal covering fraction to be. That's work that we're on, that we're basically now doing. That'll be in the follow-up study, where I'll be able to probably answer that question a bit more to say, do we match just like 1 to 2% of the expected population?